Welcome everybody to week 8 in review. We covered an important topic in this week. We went back to, from chapter 7, back to chapter 6.4 to cover something called integral action. This is putting the I in PID. So it is very important. Now let's before we get to what this is, let's talk about reference tracking. So here is a picture that the block diagram that we drew in class. We have a reference signal, and you can think about this as say the setting for your thermostat or your cruise control, or any desired, say the desired concentration. Sorry, the desired concentration of a drug in a vital organ or anything like that. Okay, so it's something that we like to track. So this is called the reference signal. So again, we can just think about cruise control. This is the speed that you set, and we want to track it. So reference tracking means that we want y to converge to r, and in particular, we want the equilibrium value of y, which we will have if we have a stable system, to equal r. So let's write out the dynamics. So what do we have here? We've got x dot is equal to ax plus bu, and y is equal to cx. So now what we've done here, we've actually given ourselves access to state feedback. So k gets x. So we could have k having access only to y, and then we have to use all of the ideas that we talked about in last week's class and everything talked about in chapter 7. But I want to focus on something different, so we're not going to really do that here. So it's a complication that we now know how to deal with. So what is u? U is equal to minus kx. Right, so u is a signal that goes in here. So what is that? It's equal to minus kx plus the feed forward filter kr times r. Okay. So what happens when we plug this in? We get x dot is equal to a minus bk x plus bkrr. Now suppose that k is chosen, the feedback filter is chosen so that it stabilizes the system. In other words, a minus bk has eigenvalues in the open left half plane. This is everything that we did in chapter 6.1, 6.2, and 6.3, so I won't spend time discussing it again. Now suppose we're asked, find the equilibrium value of x and the equilibrium value of y. How do we do that? Well, we set the dynamics equal to 0. So we're at equilibrium if we're not changing, which means if x dot is equal to 0. So setting this equal to 0, we get a minus bk x plus bkrr is equal to 0. Or by moving bkrr onto the right-hand side, we get a minus bkx is equal to minus bkrr. Now, many of you are tempted, have been tempted, have given into the temptation of dividing. That's a big no-no here, because you don't know what does it mean to divide by a matrix. We don't divide by a matrix, we multiply by the inverse. And you can check for yourselves that if a minus bk has eigenvalues in the open left half plane, so strictly on the left half plane, then it must be invertible. So it is invertible. So think about that and see if you can answer why that's true. But it always is the case. So therefore, we can solve x is equal to, and note again that the order of multiplication is extremely important because generally matrix multiplication does not commute. So we're multiplying from the left by a minus bk inverse. And therefore we have a minus bk inverse, I carried the minus sign through, times bkr times r. This is the equilibrium value of x. And therefore the equilibrium value of y is just c times the equilibrium value of x, or just minus c times a minus bk inverse bkrr. Now let's look at the dimensions here. C is a 1 by n matrix. A minus bk is n by n, and therefore its inverse is n by n. B is an n by 1, and kr is 1 by 1. Therefore, this whole thing up to r is just a 1 by 1 scalar. And therefore, if we choose kr to equal negative 1 over, notice I'm dividing, but I'm dividing by now what is a scalar, c times a minus bk inverse b. Right? Notice that c is 1 by n, this is n by n, this is n by 1, therefore I have a scalar on the denominator, which is cool. Then what do we get? Basically by design, I get that ye is equal to 1 times r, or just r, which means that in steady state, we're doing exactly what we want. If we were to plot it, what would it look like? This is our desired value for r, and if I'm plotting y versus time, we'd see some behavior that looks kind of like this, and eventually we would converge. So that's all good. Now enter a new element, disturbance. And in particular, the key point, it should be obvious in the name, but the whole point of disturbance is that it's unknown, and therefore we cannot model our dynamics around, our dynamics cannot explicitly factor in what that disturbance is. So how are we going to write this? Suppose that the true dynamics, Rx dot is equal to Ax plus Bu, as we had before. This is all we know about. But then we have F times D. And why do we write it like this? Just so that the dimensions add up. So I only want to think about a scalar disturbance. So F is n by 1, and D is just a 1 by 1. So the idea is that D is unknown. Now, is there any hope that we could deal with such a disturbance for any function D? No, that's much too much to ask. So what we'll ask is resilience to a disturbance. This is called the disturbance rejection. For an unknown D, however, we're going to at least ask that D comes from a limited class of functions. And for starters, we're going to work on this and expand it. We're going to have D be a function that's, of course, 0 before time t, and then some unknown constant. So it might hop up, it might hop down. We don't know how far it goes up or down. Okay, but that's what D is. And we want to be able to, design a controller so that YE is equal to R regardless of what D happens to be. Now, how do we do this? So suppose that we just ignored it, and we just implemented that same controller that we had above. So suppose we use the same K and KR that worked so well before. What do we have now? Well, now we'll have XE is equal to, I'm skipping some steps, but you can go and fill them back in, A minus BK inverse times BKRR minus A minus BK inverse times FD. And therefore, YE to CXE is going to equal minus C A minus BK inverse BKRR minus C A minus BK inverse times FD. This part was designed to equal R. So YE is going to equal R minus an error, minus C times A minus BK inverse times FD. And this is our error. So what's going to happen, and notice that our error is proportional to D. So what's going to happen is we wanted a picture that looks like this. Here's our R target that we wanted. We wanted this, but what we'll actually have is something that looks like this. It's going to again converge, but there's going to be a steady state error here. Okay, and as you can see, there's really no way we can avoid it within this framework. So the key idea here is to augment the state. This is the fundamental idea. And we're going to introduce a new state, z. And what is z going to be? Z is going to be the integral up to time t of the error. So y minus r dt. Or another way to write it is the integral of cx minus r. Now what this allows is now my feedback, u, is going to be again minus kx, but it's going to be allowed a new term that's proportional to z. So exactly the same idea that we had before. But now we have our new state is one bigger, x and z, and therefore our feedback control is going to be proportional to the entire state, so proportional to x and proportional to z. So let's plug this in and see what we get. So we have x dot is equal to ax plus bu plus this annoying disturbance that we don't know about. Y is equal to cx. And z dot, what is that? Well, if z is equal to the integral, let me scroll up a bit so you can see it. If z is equal to the integral of cx minus r, z dot is just going to be what's under the integral sign. So z dot is just going to be cx minus r. So we can write the dynamics as follows. X dot z dot. Let me just write them out in one by one. So x dot is equal to ax minus, we've got x dot is equal to ax plus b, and let's put what u is now. U is equal to minus kx minus kiz. And whoops, I'm sorry, I forgot to add, as always, the feed-forward filter, plus krr, and then we've got our fd. So writing this out, this is equal to a minus bk times x minus bki times z plus bkrr. I'm being a little sloppy here. Plus bkrr plus fd. And z dot is equal to cx minus r. So we can write out the dynamics there together in a matrix form. X dot z dot is equal to a minus bk times x minus bki times z. And then what's z dot? It's equal to c times x plus 0 times z. And then, what else do we have? We've got bkr and minus 1 times r plus f0 times d. So, the conclusion is, which is almost magical here, is that if the augmented matrix, so in this case it's n plus 1 by n plus 1, so if the augmented matrix, which is this guy, is stable, then the system is stable, of course, by definition, and it means that it has an equilibrium. This doesn't sound too magical, does it? It has an equilibrium, XE and ZE. But just let's think about that very statement itself. It has an equilibrium. What that means is that x dot is equal to 0, and more importantly for us, z dot is equal to 0. Let's unwrap that. Z dot is equal to cx minus r, or just y minus r. So z dot equal to 0 is basically saying, not basically, it's exactly saying that cx in equilibrium equals r, or in other words, y in equilibrium is equal to r. So that means that with the augmented state, regardless of the value of d, and note that we no longer care about our feed-forward filter, KR, which is interesting. Y will converge to R as long as the augmented system is stable. And there is some homework that works on this, that gives you some practice with this problem.